Alright, so this is going to be the first video on the dark matter lectures, and we are exploring the kinetic picture of the Milky Way. I'm going to divide this into two, so I will first record the first 25 minutes and then only afterwards the second part, okay? To make, well, it's going to be all in one video, but into two parts. Alright, so let's say where we are. We want to understand what is the flux of dark matter particles going through a detector, and second, how does this affect the detector itself. So I already told you that the number density of dark matter particles is kind of fixed due to this kinetics of the Milky Way that requires a particular dark matter halo with properties giving us the quantity of 0.3 GeV per centimeter cube in the energy density of the dark matter at the sun position. What about the velocity? Well, the velocity is harder to get just from this kinematics because the distribution function of these dark matter particles could be anything. In principle, as long as they don't are too relativistic, they will keep mounting to the Milky Way. But we want to know what is the typical velocity of these dark matter particles to understand the flux. Okay, so how do we do it? Well, in principle, the most reliable way to do it is to do simulations of dark matter halos. And this is not something we can do with my iPad, so we're going to try to expand and do something a bit more analytical. So remember that we know something about these halos. We know that they have to reproduce rotation curves, okay, with fixed velocity, and I already told you that this means that the mass should grow as r, okay, to satisfy, remember the equation we had already written. So if n grows as r, then the velocity is constant in this, as a function of r, the velocity is constant. Good, so now we know this. What else do we know? Well, we expect these dark matter particles that live happily their life in the halo, interacting through gravity, to have interacted so many times that the whole situation is in a kind of equilibrium. Okay, it's not exactly the same concept of a standard equilibrium in statistical mechanics because there are not so many scattering. Scattering each one is not so efficient with this long range weak interaction, which is gravity. But still, you expect that there is a kind of virial or time independent configuration that reproduces the behavior of the halo. In this case, there is a theorem called Jeans theorem stating that the distribution function should depend only on conserved quantities, conserved on the dynamics. One of them, so Jeans theorem, the function should be a function of conserved quantities. One of the most standard conserved quantities is energy. Okay, so let's see what happens if we have a function of energy as the distribution function. So we can check one, which is the one that we have seen before, and why not? Let's try it also here. Let's try that the distribution function as a function of velocity depends on the energy, and of course there should be some normalization factor. The energy of this configuration, it is the kinetic energy. Okay, let's say energy per unit mass of each of these particles of momentum p, and then the gravitational potential, okay, phi. All right, so let's see what happens now. So if we imagine that this is the typical distribution function for how particles are distributed in a particular place in this halo, okay, we can now compute the energy density as integration of same thing we did in the past, f of v. All right, and this is, well, once you plug the energy into here and now this back into here, what you find is that the energy density is going to be proportional to the mass, and a factor which goes out that doesn't depend on the velocity, which is e to the plus phi over E0, and then some integration, okay, of the rest of the distribution function. But all this should be normalized, so all these integrals here are just normalization factors that don't depend on R. The only thing that depends on R is the potential at which you are evaluating these ansatz for the distribution function. Okay. Now, how do we proceed? Well, we want this to be the energy density sourcing the whole gravitational potential for the halo. So that means that if you remember from Newtonian dynamics, the Laplacian of the potential of the gravitational potential is sourced by 4 pi j rho. Okay, let me put some space here. But now we know rho, and rho is a function of gravitational potential itself. Well, let me use the same letter. And here we have finally found an equation which is only depending on the gravitational potential, and you can solve it's a equation that you can solve. In particular, you assume spherical symmetry. Okay, spherically. Then this is nothing but an ODE that you can solve easily. And the solution turns out to be rho equal to E0 divided by 2 pi j r squared. So please check it. And this is great. So this hypothesis we had for the distribution function up here indeed reproduces what we expected, that mass in this kind of equilibrium state of the halo grows with r, okay, because it's rho. Remember, rho, this is rho, is basically mass divided by r cubed. Fantastic. Is that the real distribution function? Well, not really, and indeed, this is not even the real profile of dark matter halos that you see in simulations. In simulations, you see something that is called Navarro-Friend-White profile, which is parameterized by two constants. One is the a typical scale of the density, and another one a scaled distance. Okay, so you see that when R is much bigger than Rs, this grows as 1 over R cubed, and when R is much more than Rs, this grows as 1 over R. So it's never really R squared, but in the middle of these two regimes there is something similar. What is a realistic distribution for momentum, for velocities? Well, it is also given by something similar to what we wrote. And if you put the normalization factors where they should be, you can be very specific. The important thing is what I'm going to write now, so this is really a velocity. All right, and then this is only true for velocities below the escape velocity. So if you are in this halo, particles which are very fast, we are going to evaporate. They're going to leave the halo. So there shouldn't be any particles above certain velocity, which is called escape velocity. All right, and with these two numbers, you can try to parameterize the state of dark matter in different places of the halo. All right, of dark matter. Very good. I give you in figure 12 a realistic picture of f of v, and you see that, well, you plot what it is close to the profile I wrote, but not quite. Okay, you have to be a bit careful with these more realistic possibilities in the dark matter halo as having some I don't know, galaxies that have already interacting with our galaxy and generating some debris or many other things, or hurricanes, things which are not particularly easy to understand, well, easy to derive analytically. You need data or simulations for them, but in principle, the average energy density is, PDF is probability distribution function is what I wrote here. All right. So this means that the average velocity, you compute the average velocity in a rest frame where you have derived this distribution function is 0. So you take all the particles, they go from all directions, basically averaging to 0. But the solar system is moving in this frame where particles are averaging to 0. So that means that there is a extra piece of velocity, okay, as if you move in a medium which is still, you will see a wind because you're moving with respect to it, and this is basically meaning that if you go change frames, the typical velocity of dark matter particles that you see on Earth is the same as the velocity that the Earth, or in particular the Sun, has when it moves around this dark matter halo. So there is this halo, and the Sun is moving as the galaxy is rotating with a certain speed, which is basically, the speed of light. This should be the speed of light. All right, so as I said, this corresponds to the velocity of the Sun around the galaxy. All right, this means, by the way, to compute this, you need to change frames. So what you want to do is to compute not the average velocity, but you have to change frames to the frame V. It's very simple. So you need to change from the frame of at rest of the velocity to the frame. Is this x of the Sun? Okay, so it's basically, you can just boost if you want. It's going to be position of the Sun plus velocity of the Sun time, no? Okay, so if you want the velocity that you need to compute is simply the velocity at rest plus the velocity with respect to the Sun. Yeah. Okay. Okay, which corresponds to what I just wrote here. So the velocity that you want with respect to the Sun is the previous velocity plus the relative velocity of one frame with respect to the other. All right, so that means that once we have these numbers, okay, you can also plug in the velocity of the Earth as it rotates around the Sun. This is going to be very important because this is used for what is called annual modulation, and this is of the order of 10 to the -4 the speed of light. Okay, you want the average velocity of dark matter particles with respect to the Earth. Finally, this means that the flux is given by what? Number density multiplying average velocity of the Sun 10 to the 7 GeV per meter divided by centimeter per second. Okay, this is just some units that are random, but yeah, this is the kind of flux that you have in your laboratories coming from dark matter. So not too much. M is the mass here, by the way, and this is not the meter, so mass. Yeah. Per centimeter per second. Okay. Very good, very good. So square, of course, this is a flux, centimeter square per second. Once we know these numbers, okay, the next thing is to compute how do they generate scattering events in a detector. For this, we have first to do some kinematics. And remember that the energy of the dark matter particle is going to be given by simply number, the typical kinetic energy. And if you do a scattering event of dark matter with standard model particles, okay, you can compute that the recoil energy of the standard model particle or nuclei or whatever is going to be given by this quantity. Okay, this is, as I said, an exercise in kinematics. Yeah, let me write it this way. Cross 1 plus cos theta divided by 2. All right, and we see that the maximum energy that you can get, cos theta is the, of course, is the angle after scattering, right? And you see that the maximum energy happens when this angle, okay, when 1 plus cos is maximum. And in this case, what you can see is that the maximum recoil energy is of order of the kinetic energy. Okay, you really smash things and all the energy goes into the standard model part, the nuclei, then the maximum energy of the recoil is at most the energy you had at your disposal from the kinetic energy of the initial particle. Okay, so you put numbers in, this corresponds to 10 keV. So assuming that the mass of n, which is the standard model particle, I'm talking about particle, but I'm really, in my mind, I have any standard model element. In this case, the nucleons in a detector. Okay, so this mass can be, for instance, the mass of the xenon or the mass of any other element that you use as a target. Okay, let's assume that this is bigger than the mass of the dark matter. And in this case, you can simplify this formula up there and understand that the maximum kinetic energy, so recoil energy that you can have in this event, is simply given by these numbers. Okay, so this is a typical energy of a nucleon of like 80 or 100 nucleons, and the dark matter of like 10 to the, well, around the GeV scale is going to generate a recoil energy of 10 kilo electron volts. Why this 10 kilo electron volts is important? Well, because when you have a laboratory process, what you want to have is that you had some particle at rest, dark matter comes, and then there is some recoil of this one, and this recoil has some energy, and this energy is what characterizes the event, and it has to be above a certain threshold for you to be able to detect it. All right. So, for instance, the typical xenon detectors operate at thresholds of around kilo electron volts. So what does it mean? That for these events to be detected, no matter what you do, okay, the dark matter particles should be around, few or hundreds GeV. Because otherwise, the recoil energy you have is not enough to generate a signal in this case. You can try to go to lighter elements, okay, and then you can modify this denominator here, you can try to use electrons as targets or other targets which don't excite, don't make new, again, elements recoil, but for instance, phonons recoil. But this is a whole world I'm not going to touch. But this is the way if you want to go to masses which are smaller than few GeV, okay, that's what you have to do. Well, okay, so few GeV, I put 10 to the 2, but indeed, this is really few GeV. Here we are going to take the traditional GeV scale and these traditional xenon detectors and keep exploring how to see the signal in the dark matter. Of the dark matter. First, remember that this scattering is going to be coherent. Why? Because the Broglie wavelength of the dark matter is much bigger than the size of the atom. Okay, I think I need some water. I'll be back. Sorry. Okay, that means that the dark matter, so the atom sees the whole dark matter as a single event, as a single particle. The dark matter doesn't interact individually with each of the nucleons. And what we want to compute is the recoil, okay, energy. Sorry, given an event, we can compute the recoil energy. It's something that you can measure in the lab, and eventually you can compute the number of events per recoil energy. So the important observable is the rate per unit of this observable, of the recoil energy. So you want to compute number of events, rates of events per energy of recoil. So it's something, as I said, you can measure things which are more or less energetic. So this is a very important observable. This is going to be given by number of targets, number density of dark matter particles, a cross section, but not a cross section along the cross section, the derivative of the cross section with respect to the energy rate. So this is the only place where energy of recoil, that's the only place where this appears. And finally, this is, the flux is the important thing. So the flux has some velocity, and all this is average over the distribution function of the dark matter particles, right? And we're gonna compute this in the following lesson. So for now, let me give you some extra information. So this average, as I said, is nothing but and there are some simplifications that one can make. First of all is that the first of them is that from this expression here, up here, you can compute the derivative of ER with respect to cosinus, right? So this is also standard in the literature. Where mu is the reduced mass. Cool. And very importantly also, you can compute the cross section as a function of theta in the non-relativistic limit, and there is a theorem saying that this in principle is a constant plus order V effects. So in principle, if you forget about this because those are small, you can integrate this equation and find that sigma is nothing but, so this sigma over d cos theta is nothing but the cross section itself divided by 2. Okay. What else do we want to know? Well, in this integral here, you don't need to integrate all over momenta, but only from the escape, sorry, from some minimum velocity to the maximum, which is going to be the escape velocity. So you don't have states with velocities bigger than those that, as I said, can escape the dark matter halo. That's very important. And finally, with all this information, you can compute the integral from a minimum velocity to a maximum velocity of dv fv d sigma d er. Okay, and this is going to be using the expression that I just wrote, proportional to from minimum to escape here you assume that there is spherical symmetry. Here you have to plug the Maxwellian distribution I was using before, and for this guy it is going to be a constant, okay, of the angle, so you can take it out of this integral, and finally perform this integral, at least perform it up to some constants, okay, up to some order, I mean up to some normalization factor. The important thing is that it turns out to be relevant only at low velocities, okay, because it is an exponentially suppressed thing. So the dominating part of the integral is this one, and it integrates to the energy of recoil divided by some zero energy. What is this zero energy? So I didn't tell you what the minimum velocity is. The minimum velocity is there because not all the particles in this distribution are going to generate a signal. Only those above threshold that have enough kinetic energy to generate the signal need to be integrated over. So which are those particles? So those are the particles, okay, for which the recoil energy is bigger than this one, okay? So only enough particles with enough energy are gonna be relevant, and when you turn everything into the correct dimensions, you find that indeed this E of recoil appears in the exponentially suppressed rate here, and normalized by a constant E0 equal to a number. Okay, and in the next half an hour or 20 minutes, I will elaborate a bit more on what this means. So it's gonna be after that. I mean, there's no pause, but yeah, I think I see you in a bit. All right, so we continue now in a different room. Where we left it, we were exploring the differential rate with respect to energy. And remember that we were just exploring the quantity, one of the quantities which is important for this, which is the integral. Okay, we have to compute here, okay, in order to evaluate the rate per unit energy. And this is going to be shown in the sensitive curves of the detector. And in particular, the last calculation we made tells us that given an energy of recoil, okay, if E0 decreases, okay, then this factor grows and the exponential separation is higher. This is something you typically see when you look at sensitivity curves for dark matter detectors, because you see that at low masses there is an exponential, okay, an exponential separation coming from the fact, again, that the mass of the particle, of the dark matter particle, enters into this quantity. So it makes E0 decrease when you go to small masses. So this is the mass, and this is the cross-section that you typically can constrain. And again, if you go to low masses, you lose sensitivity. You also lose sensitivity at high masses, but this is because at high masses the number density, okay, becomes smaller. Since we have fixed the energy density, remember 2.3 giga electron volts per centimeter cube, then this other part of the sensitivity curve is simply coming from the less abundance of more massive particles. Okay. You can, well, now play with numbers. For instance, for the xenon detector at m dark matter of order 100 GeV, E0 is 50 keV. All right, and that's what you see in many plots for the xenon detector, that the typical range of, well, you can of course do this better, but it's around 100 or 10 giga electron volts that you start being less sensitive. Okay. Okay, so now what we have to compute, what we're going to finish this lesson with, is with the differential cross-section that we have to compute. So we now need to model a bit more the dark matter component. So let's introduce some Lagrangian, okay, for the events that we want to compute. So there is some event, dark matter going into standard model, and then this will come from an effective interaction that normally is going to have some form, and here some quark, here are some quark operators. Okay, so this is basically, oops, the vertex, and here are the four legs of the diagram. And there will be, of course, some coupling that may depend on the momentum, on the mass, on many things. All right. Now, what do we want to compute? Well, the cross-section, right? That's the only thing that is missing. The way to do it is by using quantum field theory. We are going to do it in a also pedestrian way, and I'm only going to do it for two particular examples. But what we want is the interaction not with the standard model particle, but with a nucleon. Okay, we want to know indeed the cross-section with nuclei, with the nucleon and with the nuclei that we are exploring. So in particular with xenon or any other element. So for this, what we need to compute is the matrix element not with quarks but with nucleons first. Okay, this is something that nuclear physicists do for you, so you don't need to worry too much about it. There are very advanced techniques to find it, and for this you want finally to compute the cross-section with the atom. Not the cross-section, the matrix element with the atom, okay, as composed typically, well, not typically, as composed by a number of protons and a number of neutrons. Okay, now if the scattering is coherent, all the protons and neutrons inside of this nucleus are going to see the same dark matter particle, and the total matrix element can be formed by taking the atom as a sum of nucleons, okay, and simply, using this expression that we have found before. Okay, it can be plugged in here after we take the nucleus as a collection of nucleons. This is not the case for all interactions. Sometimes there is no coherence in the scattering, like for instance when some of these atoms, when the interaction depends on the spin of these guys, the things are a bit more complicated. This is one of the things that a practitioner should take into account. Okay, we're going to see it a bit more in the next minutes. Okay, so we continue with the evaluation of this matrix element, and I was saying that there are processes which are coherent, which are those for which the scattering element of the dark matter sees all the nucleus or the nucleons as adding up in the total cross section. So the cross section with the atom, or with the, in this particular case with the nucleus, is basically enhanced by the number of elements, let's say number of protons. So that since it is a cross section, this is a square, and this may happen if you, for instance, couple to the mass or to some quantity which is basically adding up in the whole nucleus. And incoherent, in this case, each of the nucleons may contribute with a value which doesn't add up, like for instance with the spin. They have different spins, each of them will be up or down, so the average spin is not going to be 0, but it's not going to be either proportional to a number of nucleons. So in this case, the scattering with the atom or with the nucleus is basically proportional to the scattering with the nucleons. So two paradigmatic examples are those given by these effective Lagrangians. First, spin-independent coupling of dark matter with quarks, let's say, and another one, spin-dependent coupling of dark matter with quarks. In this case, you have to put here some spin. Okay, so let me do it better. Number 5, here also gamma 5 and the quark. Okay, now to compute the final matrix element, we first need to compute these form factors. So for instance, what is the value of, see, to take this kind of average, what's the value of the quark current evaluating on protons? And this is something that nuclear physicists do, or you can do a measurement also to try to see what it is, and we can evaluate it in terms of a mass of the proton and a number. Okay, and once we have it, we are not interested on this. We are interested on understanding what is the matrix element with the total nucleons and nuclei. And for this, it is relevant. What people normally do is to translate this into an effective coupling, not with quarks, but with protons. Okay, so you can basically translate the coupling G S I quark, okay, into a coupling G proton, for instance, and the here there will be what is called a factor that tells us what is the typical mass of a certain quark in the proton. Okay, and this is given by an expression that I'm going to pause to write, not to lose time. Okay, here it is. Okay, I hope this turned out okay. Yeah, the final expression, okay, for this quantity depends on the form factor that you have for each of the quarks, and you have to sum over quarks. All this is in the notes, equation 84. It's not super relevant, of course, that we know how to derive it. The important thing is that given the coupling, okay, to quarks, you can derive what is the effective coupling to protons, and the same you can derive for neutrons, sorry, for protons and neutrons, and eventually that means that the matrix element can be written as a matrix element on an atom, okay, with an effective coupling to protons. So you can forget about this G here because everything is encapsulated into this number, but yeah, if you want to, you can keep it. In the notes, I just write, I don't write it, so in the notes I write this coupling this way, okay? So let's keep the same notation. And an analogous coupling for neutrons. What's the advantage of this? It is that now you have an atom with a certain nucleus. Then to evaluate it, you just need to know the number of protons and the number of neutrons, and eventually this evaluates to quantity. So this is in the nucleus. It evaluates to assert this number. Matter. Here there is still some matrix, so some operator for the nucleus, and there is also an extra function which has to do with the coherence of the scattering. So basically, if the momentum is very high, you are not going to see the whole atom, the whole nucleus as coherent, but if it is large, yeah, you see the whole atom as a single target, okay? Right, so these are all tabulated, so you can, people who do dark matter detection, they have them in some books or some tables. And finally, okay, well, this is going to be order 1. So finally, the expression that we want, remember the cross-section per recoil energy, can be written in the following way. Okay, quite simple. At least, yeah, once you know these form factors and the this FQ function, all is known. Okay, very good. This is for the spin independent case. As I said, as you can see, indeed it is enhanced by these numbers. Okay, for the spin dependent case, this enhancement doesn't happen. And you can derive a similar result for the previous effective Lagrangian. Okay, this is the mass of the nucleons. This is the mass of the nucleus. Here some average quantity, and again some function telling us about the coherence of the scattering. Okay, I mean, I don't want to insist on this formula. The only thing I want to insist of is that there is no here anywhere an enhancement by the given by the number of nucleons. Okay, so this is basically a cross section which is going to be harder to detect because no matter how large, I mean, what you want to have is something with a lot of spin, right? But spins are not so much enhanced as just when you put mass together, where then the enhancement is proportional to the number of stuff that you're putting together, right? The spin typically tends to align or in ways that reduce it in a when you pack it in a in a nucleus. That was a bit not the best explanation. All right, so once we have all this, we can continue. And finally write things in terms of the cross section that is plotted in the searches for dark matter, which is not this one, but it is the one. Okay, this is the cross section that people like, is the cross section per nucleon. Okay, the dark matter Nucleon. And the reason is that you want to compare different experiments which have different targets. So you don't want to compare the scattering with the different atoms, but with the different nuclei, but with the different nucleons, for which all the experiments have sensitivity. And in particular, one can do this translation of scattering rate, cross-section, with a certain nucleus. One typically relates it to, in the case of spin independent, with the one that is plotted, this one, by some factors, which are standard, but you see that basically it is reduced by a factor a square. All right, and this is what is plotted, as I said, in the WIMP cross-section versus mass of dark matter, and I invite you to see what it is in the notes. Typical values for like GeV achieve 10 to the minus 44 or something centimeter square. All right. Now, there is a big challenge in dark matter searches, which is that there is also a background scattering with the elements, which is given by the different neutrinos, sources, in particular those coming from the sun. That means that if you want to detect anything below a certain cross-section, it's going to be harder because neutrinos are already producing this recoil that you are looking for. So this is a challenge for observations, and people are indeed trying to look for it and try to find ways to overcome this difficulty. So finally, before moving to the next topic, the question is, shall we build a dark matter detector? Well, I guess the answer is yes, because many of you are doing it. And the answer is depending on what is the cross-section that you're looking for, whether you can detect it or not, given a standard or a bit futuristic configuration. So for this, you can consider an interaction of the ones we wrote before, and that generates a cross-section with protons, given by here the as cross-sections typically are given by the reduced mass of the process, some interaction scale, and you can put pi if you want. And this, if you take protons, let's say GeV square, and now here something close to the WIMP scale. The question is, can this be detected? Well, we already know that these kind of masses are going to be detected in in detectors that are sensitive to kiloelectron volts. So this is a good thing. And also, now the question is, how many scatterings are you going to have per unit time? No? Are you going to have enough of those to generate a signal? So now the number of events we will have for this candidate is going to be given by the scattering rate, multiplying by time, is 1 day, and the number of targets in the detector. So if you have plugged the previous numbers here for 1 day, and you take the number of targets in the detector as kilogram per 100 GeV, which is the typical mass of a nucleus, what you find here is that you're going to have 10 to the minus 2 events per kilogram per day. And this corresponds to mass of the dark matter around the giga electron volt. And that's the second part of the WIMP miracle, that you take cross sections corresponding to the Wick scale, and then you consider mass of dark matter around the GeV, the detector that you have to build, if you are sensitive to kilo-electron volt, will have enough events for you to win the Nobel Prize. So that's why people are very excited about this possibility for the WIMP paradigm. And we're gonna stop here, and we'll continue in the next lesson with a totally different paradigm of dark matter. Thank you.